All right, can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. We're here back on site in Jenny Jump State Forest in Hope, New Jersey. We're going to have a lovely presentation tonight, even despite the clouds' attempts to spoil the mood. With that being said, well, I think I saw a couple people wandering down over there. Give them a chance to come here. You can check us out on our website, uacnj.org. That's where you're going to find a list of all our upcoming talks, any special events we might be holding, as well as a list of all our member clubs, because our goal is to reach out to as many people as possible and get them interested in space, astronomy, and science. And the best way to do that is to find someone local, because it's sure more convenient to drive 15 minutes away from you than 3 hours. In addition, you can check us out on our social media pages. We have Facebook, Instagram. We have a Discord channel if you want to share any astrophotography or even ask questions about telescopes or your setup. You can also, since we are a nonprofit, you can support. All donations go to helping pay the bills. I was saying keep the lights on last season, and people were like, "We don't want lights on. This is astronomy. We want to be in the dark." So, fair enough. We like paying the bills, or at least pretending we can. So, with that being said, since I don't see anyone wandering down this way, for people here, if you need to use the restroom, that is the porta potty in the back. To my left, your right. In addition, I'll be manning the museum and gift shop area. Also, to my left, your right, outlined in red here. After the presentation, because still they have not given me the power to be in 2 places at once. Also, when we go to leave here, we are using our head. We don't like getting run over. We also don't like seeing people get run over. It causes a lot of paperwork. Let's avoid paperwork. Save some trees that way. In addition, if you're walking around, there might be a telescope open, which you'll be able to see, you know, the telescope setup that you would have gotten to look through had the weather cooperated with us. Um, as we're walking around, any flashlights or lights we might have, please keep them pointed towards the ground, because even though we're using our headlights, we don't need to unnecessarily blind people. And with that, we're going to get into tonight's talk, which is some strange objects in the universe with Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. And Walt has been a member of North Jersey Astronomical Group and the Rockland Astronomy Club, and has been volunteering here at Jenny Jump for well over 20 years.
Longer than I'll admit to.
Which is why it's been 20 years for a while.
Yeah.
And with that, here's Walt.
Thanks a lot, Kim. Hi, thank you. Thanks to everyone online for dropping in. And thanks especially to you folks who have braved the cold. And now I'm hearing a couple of raindrops. So thanks for coming out. I really appreciate it. It's a lot of fun when the skies are clear, but I'll try to give you a couple things to think about. You know, I've named this talk some of the strangest objects in the universe. Nice hype title for you. Truth is, with our advancing technology, everything's looking stranger and stranger. You know, as much as we answer questions when we have more powerful telescopes and we look at different bandwidths, there's a lot more questions that are popping up. And astronomy is just such an interesting field to look at. Just about anything you look at up there is strange. So I'll give you a warning. I'm going to look at some stuff in the solar system, some stuff in the galaxy, and then some stuff outside of the galaxy as well. And, you know, when I do these talks, my hope is always that there's some topic that I cover or something that I cover that will get you looking it up on Wikipedia or just Googling it to get more information. So that's my real hope. Quick science lesson before we really dig in. I just want to talk about the electromagnetic spectrum, because our telescopes can see so much more than our eyes. If you look at this diagram, this little bit right here, that's what we can see with our eyes. And we have infrared, microwaves, and radio waves on the longer side of the spectrum, and the shorter side, which gets more and more powerful, ultraviolet, X-ray, and gamma rays. So a lot of the stuff we're going to look at is filmed in the infrared or in the ultraviolet. And some of the photos that you see, whether it's in the newspapers or online, are really a composite of visible light with usually infrared and sometimes ultraviolet thrown in. And astronomers color those wavelengths beyond what we can see, different colors to represent different things. But that has really helped us. And another thing to think about, when we look out, far out into the universe, the further out we look, we're looking back in time. We're actually time traveling. Because if we're looking at an object that's, say, 1 billion light years away, it means that it took that light that we're seeing today 1 billion years to get here. So we're not seeing that object as it actually is today. We're seeing as it appeared 1 billion years ago. And that's kind of an exciting thing too. That's how astronomers, by looking deeper and deeper into the universe, can start to see how galaxies form, because they're looking at galaxies. We've seen a galaxy that's within 400 years of the estimated Big Bang, which is just amazing. And one of the surprises is some of these galaxies are much more well developed than we ever thought they were. And so that was one of the many surprises. So take a look at these two pictures. This is the Eagle Nebula. It's an area of the sky that gives birth to stars. The way stars form is clumps of gas like this. One of the ways they form. Clumps of gas like this compress until they heat up, and a protostar ignites, and then a star will be born in that. When the radiation of the explosions, the nuclear fusion, goes out and equalizes with gravity, we have hyperstatic equilibrium, and so the star steadies out for most of its life until it starts burning up all of its hydrogen, and then it starts acting wonky again. But on the left is a Hubble Space Telescope picture taken in visible light. So that's what it looks like in visible light. On the right, Hubble Space Telescope with its near infrared. And you can see it's quite a difference. Both of these photographs or images give us different information. And the infrared helps us cut through a lot of the dust clouds that obscure our vision of what's going on. So, great illustration. These are both near-infrared images. It's just that the Hubble, they're slightly different wavelengths. The one on the right is the Hubble Space Telescope, and the one on the left is the new James Webb Space Telescope. And if you come back in July, I'm going to be doing an update on the James Webb Telescope. We'll have about 2 years worth of images this summer, and I'll talk about what we've learned and look at some of those images. And you can just go to James Webb Space Telescope website yourself and see it before I even open my mouth. One of the interesting things about this Eagle Nebula, and it's not one of the strange objects, their nebula are very common, but one thing that I find interesting is that there's a very hot cluster of young stars right up around here, and that's where you're seeing all this illumination coming from. But it's also causing this gas cloud to erode, and so these pillars are actually the most dense parts of the cloud that have not eroded from the intense radiation coming down. And scientists studying that cluster think that a star went supernova about 6,000 years ago. And these pillars are about 6,500 light years from us. So if the scientists are right, we're going to have to wait about 500 years until that light of the supernova gets to us, and we can see if these things are still in existence or not. But right now they look like they're in existence. So let's get to my first strange object. Anyone have any idea what that is? It's the famous hexagon on Saturn. That's actually in our solar system. And it's hard to believe that something like that would form naturally. It's at about 70 degrees latitude. And this photo is from NASA's Cassini mission. So you're looking at a whole bunch of cloud structures with numerous vortices. That big purple thing in the middle is a giant hurricane right on the North Pole. And the eye is about 50 times larger than any hurricane we've seen on Earth. The hexagon and the hurricane spin in a clockwise direction. But some of these little vortices we see here, and there's a whole bunch of them, here, and here, some of them go counterclockwise. And, the largest one, that white oval down below, is spinning counterclockwise. It's about 2,200 miles around that hurricane down there, which is twice the size of the largest known hurricane on Earth. And like on Earth, the hexagon it's a current of, well, you'd say air, but it's not the same air that we have. It's a much different chemical composition. But the weather features share very strong similarities to the weather patterns or the weather objects that we see on Earth, namely hurricanes and tornadoes. And as you know, those are notoriously turbulent and unstable. A hurricane on Earth lasts, a week, maybe 2 weeks if it's a long one. But this has been there for decades. And who knows, maybe centuries. The Pentagon was discovered in 2006, and it shocked us that it even existed. Um, the planet's high winds, which reached 300 miles per hour, you'd think that it would disperse something like that pretty quickly. No one would expect such a perfect geometric figure. And after it was discovered, JPL and NASA went back to old films that the old Voyagers took when they passed by in the 70s, and they could see that that hexagon was there. So they know that it was there at least to the 70s, and as I said, who knows how far back that goes. So that's interesting and very beautiful object sitting on the bottom of Saturn. This is an illustration of Jupiter and the moon Io, its closest moon. The European Space Agency did this animation just to show the magnetic lines of Jupiter and how they interact with Io. Io is an intense magnetic field because it's so close to Jupiter, and it's the most volcanic planet in our solar system. It releases about a ton of sulfur dioxide every second due to this volcanic activity, and the sulfur dioxide becomes ionized. It means it gets charged, and it gets trapped in Jupiter's rotating magnetic field, generating an ionized plasma torus. So there's a ring of ionized sulfur around Jupiter. It's a hazy yellow ring that we can't see with our telescopes here as amateurs, but it's only part of the uniqueness. You see the toroid there? That's the sulfur cloud that's caught within there. But Io is just a very interesting planet in itself. There's a real picture of it, and you can see from all that volcanic activity, we see all that sulfur dioxide staining the outside of Io. As I said, it's the most volcanically active body in the solar system, with 100 plus active volcanoes at any given time. There's at least half a dozen erupting at any time. So the face of the moon it's always changing. You're always getting a different photograph when we get pictures of it. And the sulfur is a result of those eruptions, that yellow color. But that's not all. Io moves so fast that when you look at it from Earth, you can see movement within an hour or two. And astronomers get these maps of Jupiter and the moons, and Io, of course, is the closest. The 4 Galilean moons are usually on these maps, and we can tell when a moon is going to go behind or in front of Io. And you can actually see the shadow of Io when it passes in front, and you can see it just blink out of existence as it goes behind Jupiter, and then hours later come out the other side. So it's pretty cool. Io orbits Jupiter at the same distance that the moon orbits Earth. So they're at about the same distance, and they're also about the same size. But the moon takes 4 weeks to orbit the Earth. Io takes just over 42 hours, right? So 4 weeks compared to, and 42 hours. And of course, Jupiter is much larger, right? It's 318 times as massive. And it's 1,000 Earths can fit inside of Jupiter. The reason why it's 318 times as massive and not 1,000 times as massive is because it's a gas giant, so it's not as dense. And so there's less density there. So Jupiter whips Io around at about 38,000 miles per hour compared to our moon at 2,200 miles per hour. And if Earth were the size of a nickel, Jupiter would be a basketball, just to give you an idea. So let me give you another quick science lesson before we think about our next strange object. Almost all comets have an elliptical orbit, as do the planets. And by elliptical orbit, I mean they're not perfectly circular. The planets aren't, and the comets aren't. Comets come out of out of the Oort belt or from the outer reaches of our solar system. They come in around the sun and then back out. And the amount of time it takes for them to go around the sun once and come back to the same position is called its period. So Halley's Comet is about 76 years. There's some comets that have, like Tempel 1, has a 5-year period. And Comet Hyakutake, which we saw in the 90s, has about a 17,000-year orbit. But they all come back. So I don't pretend to know a whole lot about the math behind this. But we look at the eccentricity of the orbits. Right? If the eccentricity of the orbit is 0, it's a perfect circle. If the eccentricity is between 0 and 1, it's an ellipse. It's an elliptical orbit known as a negative energy orbit. That means that's what the comets and that's what the Earth and all the planets have. The planets are much, they're about 0.2, 0.3. Comets have a much larger elliptical orbit. But they're all under 1, which means that they circle the sun and they come back. At 1, we have a parabolic orbit, and the object can escape the solar system. After 1, we have a hyperbolic orbit, which means that it will leave the solar system and has probably come from another place. Some comets can change into a parabolic orbit by getting a little boost from a planet and then shooting out of the solar system. That's not very common, but it has happened. But back in 2017, we had this strange object called Oumuamua. Oumuamua. It's at first we thought it was a comet, then we thought it was an asteroid. I think we're back to a comet or an unnamed object. It's just a strange object that ran through our solar system. And because of its trajectory, we knew that it came from outside our solar system and was going to leave our solar system. And Dr. Robert Work was using the Pan-STARRS telescope on Mount Haleakala on the island of Maui, which I was lucky enough to see. Very, very cool bunch of telescopes. The Pan-STARRS, one of its major jobs is to go look for asteroids and comets that might come too close to Earth or might even collide with Earth. And so that's a very specialized telescope. And it found this object. We named it Oumuamua, which means scout, or a messenger who arrives first, which is kind of a it's kind of a creepy name. It was first described as a cigar shape and reddish in color, and it's about 167 meters wide and about 1 kilometer long. So it's 10 times longer than it's wide, and we have not seen that type of proportion on any asteroid or comet. So it's very strange in that, and also it varied in brightness by a factor of 10 as it spun around on its axis every 7.3 hours. And that's something that we just haven't seen in comets and asteroids, that kind of difference in brightness. So both the Hubble and the Spitzer space telescopes tracked it going at about 85,000 miles per hour relative to the sun. It was traveling so fast that it definitely was not gravitationally bound to the sun. We knew that for a fact. And therefore, it came from interstellar space and would return there. In August 2018, a study from ESA, the European Space Agency, the Gaius telescope, identified 4 stars that Oumuamua could have come from or come close from, and maybe they're one of those systems was its home star. We just don't know. It was here quickly, and it left just as quickly. This is just another artist's rendition. There's a bunch of theories about what Oumuamua is. An early theory was that, as I said, it was an asteroid, but scientists discovered that the sun's gravity was not the only thing propelling it. It seemed to have gotten uh, some of its velocity from another source, and that led people to think maybe there was some trapped ice here that was sublimating. The sun was melting it, and they were getting some gas jets that was pushing it a little bit. That's what this artist is trying to show. But it wasn't enough to think it was a comet, because we didn't see any tails. We didn't see an ion tail. We didn't see a dust tail. It's just a very strange object. And of course, people started speculating, extraterrestrial. Even a Harvard professor uh, speculated that it might have been some sort of space probe when we first saw it. So currently the consensus is that it's some kind of comet with extra propulsion coming from that hydrogen jets caused by sublimated ice. So we've seen a few comets, as I said, get a gravitational boost from passing planets and then leave the solar system. But looking at all the options and looking at the high speed, also looking at where the direction that Oumuamua came from, which is called the solar apex. It's kind of like where we're heading towards Lyra, the constellation Lyra. That's from the direction you would expect it to scoop something in, or something to enter our solar system. So I'll conclude with a quote from NASA. He said, "Oumuamua is the first confirmed object from another star to visit our solar system." So this is a topic that's worth Googling. It's very interesting. There's no absolute consensus as to what it is. It looks like it's a piece of rock, and one of our first interstellar visitors. We don't see objects coming like that. Although I did read one scientist said, we probably have had a lot more, but they move so quickly and they're so small, we probably haven't detected it. This was very close to the sun by the time we detected it. It got really close. So while we're on the subject of strange objects that some people think might be alien structures, and I'm just putting that in for interest. I don't think they are. I think when we look at them long enough, we figure out what they are. But they're still, whenever people don't understand what it is immediately, it seems like alien structures and alien visitors always creep into the possibilities, as incredible as they might be. So this is a star called Tabby's star. It's an F-type main sequence star. It has a red dwarf companion. That means a very small, very cool star that will probably be around for 1 trillion years as it cools off. It's in the constellation Cygnus, about 1,400 light years away from us. And the red dot shows its approximate position. And by the way, here this is Lyra, so that's the direction that Oumuamua came at us. The other object I just spoke about. I don't know. This must be a troublesome area of the sky or something. But this is where Tabby's star is. It's in Deneb, the Swan. And it was discovered around 2014, and it was named after the author, Tabitha Boyajian. This is a picture of Tabby's star taken in infrared on the left and ultraviolet on the right. Not very impressive. It's just another star among a bunch of them. But it changes its brightness in a very strange way. Lots of stars change brightness. There's an organization called the American Association of Variable Star Observers even that observe stars, and they try to plot as it dims and gets brighter. Sometimes it's because there's a planet or a companion star that passes in front of it. It's called an occultation. So if something passes in front of that star and is orbiting it, we see periodical brightening and dimming of the star. Sometimes the star is just having some strange there's some kind of mechanism in the star that's causing it to be unstable, and that it will brighten and dim periodically, and people watch that and they they record that, and it's a great way of what we call citizen science. There's a lot of amateur astronomers who belong to this organization and spend a lot of time giving data to our data banks um, about the brightness of the star and the periodicity of the stars. So there's probably 50 different reasons why stars vary. You could probably Google it. But the Tabby star and a handful of others just don't fit any of those 50 molds. They're just really unique. So Tabby star dims irregularly. It drops by as much as 22% brightness for several days at a time. And as with other variable stars, the most likely explanations are something passing in front of the star. But the brightness dips were too significant to be caused by an orbiting planet. So scientists began suggesting alternative explanations. For a while, a popular hypothesis was that the dips were consistent with a gigantic energy collecting structure that you see an artist's conception here, built by intelligent civilization. But researchers have been keen to stress that this alien megastructure scenario is very unlikely. And Tabitha herself put that to bed. Here's another artist's rendition of what a structure like that. Tabitha spent years studying the star and ruled it out. And the reason why she ruled it out was she detected that there were some forms of light, there were some wavelengths of light that got through where visible light didn't. And because of that, it wouldn't have been solid panels, because solid panels would not let any radiation through at any wavelength. So she was able to measure and prove that there were not panels like this, because we were able to see different wavelengths of light actually escaping that. This is actually called a Dyson sphere, and you'll see it in science fiction books and all kinds of great stuff. So whatever's blocking the light is not blocking all wavelengths, and so it's not a solid steel structure or anything like that. Most likely, and this mystery is still unsolved, but most likely swarms of objects like a family of comets or the remnants of a smashed moon or planet are the cause, or possibly a deep space object between the star and the Earth may be causing that. And here's an alternate guess to what Tabby star looks like with an irregular circumstellar dust ring. So maybe there's just an irregular dust ring that is really thick at parts, and that's when we see the 22% decrease in the light. So there's all kinds of stuff. There may be an unusual stellar process going on that we don't know about. We're discovering so many unusual stellar processes with our new technology that would not be surprising either. So here's a similar object. It's the Exotica catalog. Astronomers have all kinds of catalogs for stars and objects and anomalies. And this one's called VVV WIT07. And it's at the center of the Milky Way galaxy. And by the way, you know, this sounds really, I love all these, you know, highfalutin scientific labels we give objects, but the WIT stands for what is this? And if you see a catalog with WIT, it means what is this? They don't know. This is in the constellation Scorpius. So if you're here in the summertime and you're standing there, you look that direction and you will see Scorpius. You'll see the very center of the Milky Way, Sagittarius and Scorpius. This is located about 25,000 light years from us, from the Earth. And it was observed in a deep eclipse, around 80% dip in light, which is just amazing. And scientists aren't sure if it's another Tabby star or if it's what's called a Mamajex object. So an Mamajex object is kind of interesting. So if it's not another Tabby star situation and it's a Mamajex object, this object, which is named after an astronomer, Eric Mamajex, at the University of Rochester, it's a super huge ring system around a planet that eclipses a young sun like a star. In this case, it's probably a brown dwarf. So that's like a star that's, you know, larger than Jupiter, but it just missed being a planet. It was big. It was massive enough to ignite, but at a very low temperature, and so they're very hard to see. And it's much larger than Saturn's rings. Uh, you know, data shows that that in this case there's probably 30 rings or more, each of them tens of millions of kilometers in diameter. And they also found gaps in the rings, just like Saturn. You see this has a bunch of gaps, indicating that exomoons may have formed as well. If we replace the rings of this Mammajet object with Saturn rings, they'd be easily visible naked eye in our sky, and it would be many times larger than the moon as far as the space it would take up. So this system is huge when you put it in those terms. Here's another strange object. I'm going to switch gears a little bit, and we're going to look at what's called a Fermi bubble. And Fermi bubbles are about 25. These are about 25,000 light years high. This is our Milky Way galaxy, so that's about 100,000 light years across our Milky Way. There's where the sun is, and these are gamma ray emissions that we've discovered with the Fermi Gamma Ray Space Telescope. Only in 2010, so we've known about these for about 14 years now. It was previously unknown as a feature in our galaxy. These gigantic bubbles, and we call them Fermi bubbles after the telescope that discovered them. They're magenta-colored orbs. In this photo, since it's gamma rays, they had to artificially color it, but so they chose magenta. As I said, they stretch 25,000 light years above and below our galaxy. So total 50,000. So that's half as high as our galaxy is wide when you're looking edge to edge. And this photo is a composite of visible light and gamma ray and also infrared. And of course, we're looking at the Milky Way edge on here. Here's another photo from NASA's Fermi page, and I couldn't find data on what wavelengths this is, but I'm guessing this is pure gamma ray without any visible light in the picture. So we know that black holes ingest an awful lot of matter, and sometimes they produce bipolar jets. So some astrophysicists hypothesize that these are the remnants of such activity in our own galaxy. We know that our galaxy has a giant black hole in the center of it, and so they're thinking that this is the remnant of those relativistic jets that are produced when it's really having a big meal and eating up a lot of matter. This is just an artist's illustration of what I'm talking about. That's the kind of bipolar jet that's produced by a black hole devouring a nearby star and then releasing a huge amount of energy. It goes both up and down. So they're thinking that those Fermi bubbles are the remnant of activity like this. Those jets are often called relativistic jets because the matter is being ejected at close to the speed of light. So, you know, Einstein's law of relativity, they call it relativistic jets. So this isn't one of my strange objects, though, because these things are all over the place. We see evidence of these bipolar jets throughout the universe, but the mystery was those bubbles, and this common occurrence may be the explanation, but we don't know yet. Let's see how we're doing on time. Oh, great. Okay, another quick science lesson, this one in galaxies, and I just want to, this is oversimplified, but there are three main types of galaxies: the spiral, the elliptical, and irregular. And you can see the Milky Way is a spiral. So these are very common galaxies. So I'm showing you this so you can relate to how strange this next object is, which is a galaxy. This is called a Hoag object, after Arthur Hoag, the person who discovered it in 1950. The outside ring is young blue stars, indicating they're young, they're hot, and you see there's a center of redder stars in the ball in the middle. And those are almost always, well, not almost always, they are always older stars, much older. So we have two populations of stars. We have the ball of old stars and this ring of new stars, young stars. And between the two is a dark void, which really has people scratching their heads. 70 years later, after its discovery, we still don't really know what formed this object. And the circularity of the object is very unusual. It may have something to do with its formation. Again, we don't know. The object's about 100,000 light years across, so it's basically the size of our Milky Way. And it's similar in size. It's about 600 million light years away, so it's kind of distance in Serpens Kaput. And interesting enough, this red circle in the gap at 7 o'clock is a more distant ring galaxy. It's quite amazing that lined up, that we could see that ring galaxy. So one of the first theories were that we were looking at gravitational lensing. And what gravitational lensing was, it was predicted by Einstein, and that is, if there is an object that is super massive, like a massive galaxy or group of galaxies, it would bend space-time in such a way that an object behind it could be seen, because the light would travel along the curved space-time of the object. And we have proved that theory correct by seeing a lot of lensed objects. So, there's all kinds of different distances, but typically something like the massive object that is causing the curve in space-time, maybe 5 billion light years away from us, and then the galaxy behind it is another, maybe 10 billion light years away. And there's all different distances, but the massive object is always in front of it, and there's always millions or billions of miles between that and the object it's lensing. So in this picture, we see a galaxy that's behind this, and it's being lensed and stretched. It's very distorted when it's lensed. So that was one of the first hypotheses. But the center of the ring that we just looked at in the Hoag object has an identical redshift to the center. And when you look at one of these, the redshifts are much different, indicating that this is at a much further distance than this. But the Hoag object is not like that. The entire object is the same distance. And just to give you an idea, what redshift, everything in the universe is moving away from us and moving away from each other, except for a couple local galaxies, like the Andromeda galaxy, which is going to crash into us in about 4.5 billion years. But other than that, everything's moving away. And as things move away, the light gets shifted into a longer wavelength. And we can measure that. And the more the shift of the light to a longer red wavelength, the faster the object's moving and the further away it is. It's the main way we tell how far an object is. And so we were able, just by measuring the redshift, to exclude this theory that it might have been a gravitational lensed object. So here's another hypothesis, is that two galaxies collided billions of years ago, and the gravitational effect of a central bar has since vanished. You can see the bars on this cartwheel galaxy here. But that usually involves a large and a small galaxy colliding, as we see here. And you can see very clearly the difference there. A high-speed collision forces matter outward which gives us a beautiful object like this. And that's why we see, again, an outer ring of blue objects, because there was a shock wave that compressed the gas and caused stars to be born while these two galaxies collided. So NASA's website states that observations in radio waves indicate that Hoag's object, our mystery object, has not accreted a smaller galaxy in the past billion years. So NASA is able to look at Hoag's object and say there's not another galaxy that's been accreted, at least in the last billion years. And there was an article in Forbes magazine on this object, and it pointed out this type of ring galaxy has certain features that are lacking in our strange object, our Hoag's object, right? The identification of a second galaxy with distinct population of stars from the main galaxy. It's present here in the cartwheel, but not in the Hoag's object. The presence of faint fragments of a collision that should persist for billions of years. Again, we see it here, we don't see it in the Hoag's object. And a high relative velocity between multiple components of the system. So we don't see that. We see that there are different velocities in this cartwheel among the components, but Hoag, we don't see that again. So it's still a mystery. And who knows how many telescopes or how many observations we'll have to make before we can figure out that strange object. So now we're going to shift gears a little bit. Once again, I'll give you a, let me see. Hold on a second. Okay. Next month, I'm going to be doing a talk on the life of stars and the evolution of stars. I'll just give you a really quick 3-minute intro so you can kind of grasp what we're talking about next. But all stars start out as a stellar nebula, a gas cloud, and the gas cloud starts folding in on itself. The gravitation pulls it together, and it starts to heat up, and you get a protostar lights up as soon as you get nuclear fusion, and then when the force of the nuclear explosions going outward and the gravity coming inward stabilize, you have what's known as hydrostatic equilibrium. And so then the star stabilizes, and it'll stay like that for most of its life. For the sun, that would be 9.5, 10 billion years. For a bigger, younger star, it might be less than that. But for stars that are about the size of the sun, up to about 8 times the size of the sun, they take this path. They're an average star for most of their life. When they burn up the hydrogen, they become a red giant, right? The gravity starts losing out, and the gas expands. At that point, we'd be inside the sun. When the sun becomes a red giant, we'll be inside of it. And then it throws off a ring of gas called a planetary nebula that sticks around for 50 to 70,000 years. And then what's left is a white dwarf. So there's no explosion involved. There's an expansion, a shedding of about half of its mass, and then sinking down into a white dwarf, which is about the size of Earth. So picture an object that's about the size of Earth but has half the mass of the sun packed into it. So it's really a very dense object, and it just takes billions of years to cool down. What we're interested in, what I'm going to be talking about in some of the strange objects, is larger, massive stars. So up to about a massive star, 8, 10 times the size of the sun, all the way up in size, becomes a red supergiant, and it keeps burning past carbon until it gets to an iron core. When you get iron in the core, the iron requires more energy than it gives out, and within seconds you have a supernova explosion. The star collapses in itself, and you just get an amazing explosion. Again, oversimplified. I'm just trying to give you an idea of what's going on. So here's the supernova. So if it's up to about 60 times the size of our sun, what we get is a neutron star. And if it's more than 60, 80 times the size of our sun, we'll get a black hole as the remnant. So I'm going to look at a neutron star-based strange object first, and then I will look at a black hole-based. So the first, this is the Crab Nebula. It's a great example of a star that exploded and left a neutron star in its place. It's spinning around. I believe it's 30 times a second. The neutron star is about the size of the island of Manhattan, about 12 miles, and it's spinning around, sending out. We saw that bipolar jet, so it's sending out signals as the pulsars is spinning around about 30 times a second. And we call that neutron star a pulsar, and that's not an unusual object. It's very common, but it helps us understand a little bit about these fast radio bursts, which are a phenomenon that do have scientists scratching their head. They're sudden rapid chirps in the radio wave spectrum that last only a few milliseconds. Most appear to come from outside the Milky Way, even hundreds of millions of light years away. And the hypothesis includes everything from black holes to neutron stars to extraterrestrial civilizations, of course. They were first discovered in 2007, so we've been thinking about these for about 17 years. And we're a lot closer to understanding them, but we realize that the source of these radio bursts are most likely varied, as we see that the radio bursts themselves are varied. And so we're now cataloging the type of bursts and figuring out where they're coming from. Scientific American had a really good article on this in November 2021. It was very helpful to me. But we now know that these explosions, some of which produce as much energy in a few thousandths of a second as the sun does in a month, they happen about 800 times a day, spread throughout the universe. So they're pretty common. They're strange, but they're common. They happen about 800 times a day, and from all different sources. And we also know that the bright light that accompanies these explosions can reveal much about deep space, because an object that far away has to pass through a lot of objects for the light to get here. And that light signature can tell us something about the types of objects that these fast radio bursts, these FRBs, are passing through. So they can provide us, if we can really get to understand these FRBs better, they really can help us in a big way understand the universe, or at least the types of objects there. So in April of 2020, 3 separate teams of observers detected an FRB originating from a magnetar, which is a neutron star with a super duper magnetic field. I mean, a really heavy duty magnetic field. It's an extreme neutron star. It's an object that it's like the one that we looked at the Crab Nebula, except the magnetic field is so intense that, as Adam Mann notes, if we approached within 1,000 kilometers of this magnetar, within 600 miles, the magnetic field would disrupt our body's nuclei. It would tear our atoms apart. It's that intense a field. We would effectively dissolve 600 miles away from this magnetar. Just, that's it. It would rip the atoms that make up our bodies apart. So this is a very, very intense magnetic field. And they were already a candidate for the cause of FRBs, but none were directly observed. We didn't observe FRBs directly coming from a magnetar. And here in 2020, we observed it coming from a known magnetar. So that was our first information of where these things are coming from. This is another artistic impression of an FRB. Some scientists say that they saw X-ray flash following the radio signal, suggesting a very complex process. We need a lot more research, both on the magnetar and other FRBs, to understand what's going on. And it could be a star quake, maybe one of the sources, but one observation doesn't carry the day. We've got a lot more research to do. We already know that there are FRBs that are one-off events, and there are FRBs that repeat, like FRB 121102. On just one day in August 2017, it repeated a staggering 91 times. Sorry, getting this a little mixed up here. So it makes it unlikely that a single source is the cause of these events. We think there may be two separate or even more different types of events that are causing these FRBs, right? Probably two separate causes, at least, for the repeating FRB and the non-repeating FRB. So magnetars can explain some of the fraction of the FRBs, but they can't explain them all. One thing that really showed us that they couldn't all come from new magnetars is that we observed an FRB come from a globular cluster, and globular cluster typically have stars that are 10 billion years old, and magnetars settle down into regular neutron stars within 10,000 years or so. So already we see that there's definitely have to be two separate sources, a magnetar and an older star, which we don't understand yet. So the ultimate goal of scientists is, if they can understand FRBs better, they can better map matter throughout the universe using these FRBs. That's our hope, and it's going to be years away, but they're making great progress on that. We keep sending more and more powerful telescopes with different spectrum sensitive cameras there. Okay, the Great Carina Nebula. I don't want to keep you folks. So this is a jewel of the southern sky. It's a beautiful nebula. It's also known as NGC 3372. It spans over 300 light years, which is gigantic. It's one of our galaxy's largest star-forming regions, and like the smaller, more noteworthy Orion Nebula that we can see in the winter sky, you can still catch it now. The Carina Nebula is easily visible to the unaided eye, and even though it's at 7,500 light years, it's about 5 times farther away than the Orion Nebula is. The Orion Nebula we can still see. As Jupiter sets, the Orion Nebula is setting as well, but we can still see it for another probably a couple more weeks. So using a combination of image and processing techniques, astronomers created one of the highest resolution images of an extended object ever produced by the Hubble Space Telescope, and this is the Eta Carina star. It's more than 8,000 light years away, and we are able to get detail of structures that are only 10 billion miles across, which sounds like a really large area, but it's just amazing the type of detail that we've gotten here. You can see dust lanes, you can see tiny condensations. You can see this bipolar cloud here, and two relativistic jets, and there's a tight dust collar that's kind of choking that star. It's just really an amazing image. The star itself is 5 million times larger than our sun. Um, and Betelgeuse is still 300 times larger than Eta Carina. So it's not the largest star we know, but it's a massive star, and it makes our star look tiny. Um, it was the site of a giant outburst about 150 years ago, which became one of the brightest stars in the southern sky. And though the star released as much visible light as a supernova explosion, which is what you would expect it to do, just explode like a supernova and be done with it, it survived the outburst. And somehow the explosion produced two polar lobes and a large, thin equatorial disk, all moving outward at about 1.5 million miles per hour. So this is expanding at about a 1.5 million miles per hour. Apparently, there's relatively little dusty debris between the lobes, and blue light, as you can see, is able to escape. So we estimate to be 100 times more massive than our sun. It may be one of the most massive stars in our galaxy. It radiates about 4 million times brighter than our sun, and we expect another outburst from Eta Carina. And again, it is the mechanism there is a mystery as well. Back to our life cycle, we're gonna look at a black hole, and I'm gonna skip some of it. This is a black hole, artist's conception of how a black hole bends space-time so it distorts things around it. And this is a picture that became famous around 2017. It was the first photographic evidence we had of a black hole. We don't actually take a picture of the black hole because no light leaves it, but this is the accretion disk. This is the matter that is getting heated up as the black hole is eating it. And so the strange objects that are now fairly common are these galactic lenses, these gravitational lenses, and we see here that a galaxy behind this massive clump of galaxies is being lensed and very much distorted, and it makes some cool stuff. This one's called an Einstein cross. This is actually a star that went supernova, and the light from the supernova, which happened behind this massive cluster of galaxies, took 4 different paths. And so you see the same supernova 4 different times at slightly different points in the explosion of the star. And this is something that Einstein predicted we could see, and we actually have been able to capture it on film with the Hubble telescope film. We image it. We don't capture it on film. This is just a gravitational grin, gravitational lens that just makes a funny face. And here's one more where we have 2 colliding galaxies and a lot of young stars that are being born out of collision. So thank you very much for coming and sitting in this cold weather.
All right. Thank you, Walt, for another great presentation. We are going to be doing a question and answer session because I'm sure you have some questions. I know online people. So before we get on, because I saw a couple of you sneak in after the safety briefing, when we go to leave, we are using our headlights because we don't want to get run people over. If you need to use the bathroom, that is the porta potty in the back, illuminated by red. We also have a museum and gift shop area. And unfortunately, I think we did shut the roof of the one telescope, so it is still very much cloudy out, which is what I was trying to see when I was walking out the lawn. So for the people here, how question and answer is going to work is you're going to raise your hand and wave it about because I am night blind since I've been staring at screens. I have no dark vision. I'm going to start this off by our first online question. Do other planets have weird geometry like hexagons?
not as weird as Saturn. I mean, we don't see like squares and triangles and stuff. We see we do see spots like there's a great red spot on Jupiter, which you could call it a geometry. It's been there. It's a storm that's been there for probably centuries. Very interesting object, and so on Neptune there's some shapes, but nothing as startling as that hexagon on Saturn. That stands out. That we know of, right? There's lots of planets that we have not photographed because or imaged because they're not in our solar system and we haven't reached them yet.
All right. Was there a question out here? Bueller?
So do we understand why the why the shape of that is a hexagon rather than a circle? Like it seems like it should be circular with that hurricane. We have no idea why
We
it's
don't
hexagonal.
know.
Okay.
No, and you're right. You would think the way that rotate between the rotation and the winds, you'd think it would just be a circle, and yet not only is it a hexagon, but it's a hexagon that has lasted at least 30 or 40 years that we know of, and could be centuries. It's a total mystery.
And the follow-up comment to that question was, if the vortices are spinning in opposite directions, because you noticed there were a number of points here, does that mean that they're kind of acting like interlocking gears? Like, that child's toy where
Yeah.
you put the gears in and one spins this way, the other spins
Yeah.
that way.
I don't think they do. I can't honestly answer yes or no, but I believe they're just separate storms within that huge area.
Yep. And one of our viewers says they believe Saturn has one near the pole as well. Wait, we were talking about Saturn.
Yeah,
Okay.
we're
I
talking
don't know
about
what.
Saturn. I mean, if
Maybe
they're
they
talking
were-
about like a great red spot, that's a hurricane. We saw in the very middle of that hexagon that there was a huge hurricane, which is what we see in Jupiter's red spot, and they're both red.
All right. Question out there. And keep in mind, I'm kind of blind, so you kind of need to wave your hand around. All right. Our next question is, if a human from Earth could stand on Io, would they be able to detect the difference between how fast Io is going and how fast the Earth goes?
It'd probably be like Io's moving so fast. It'd probably be like surfing. But yeah, I don't even know where to go with that question.
I think that has to do with that
I mean,
you get into weird. Do you feel the motion of the train beneath you? Like you're standing still, but you're actually hurtling down the track at how many miles per hour? Sort of questions. So
yeah, well, I don't have the numbers here or memorized, but you have to understand that the Milky Way galaxy is hurtling through space at an amazing speed and rotating. The solar system is moving at an amazing speed. The Earth is moving around the sun. So, I mean, we have all these different very high velocity things going on, and I can stand up straight and not fall over.
everything in the universe is a tilt-a-whirl.
There you go.
Luckily, less of us get motion sick than we could. All right, questions? All right, so our next online question is, could Oumuamua have been a fragment from a larger object, or maybe it got hit by an asteroid which caused its tumbling and spinning motion?
I guess anything's possible, but when you look at the orbit, we had enough data to figure out where it came from and where it's going, and so it did not, as astronomers traced back where it went, where it came from. There was no mention of collisions. We looked at the stars that it might come from. It came from the solar apex, so it didn't come right through the asteroid belt. So there was no indication when we followed the orbit of Oumuamua that there was any collision. But in interstellar space, could it have collided? Sure. We have no idea.
No one knows what happens in international waters, or what happens in international waters stays in international waters.
I guess.
All right. So our next online question: if black holes ingest everything, how can they also have jets? I'm doing air quotes here. Escaping.
Because they don't escape from the black hole itself. They escape from the accretion disk. And, the matter starts spinning around very quickly around the black hole, and then when they get sucked into the event horizon, nothing escapes from there. But the relativistic jets are a function of the accretion disk.
You also have
as soon as a astrophysicist starts talking about the math, I'm done. Show me the pretty pictures, but don't give me the math.
same. One of viewers who is also astronomer says that they believe it's from matter being close to the event horizon, but not quite from the edge of no return.
Right. The accretion disk.
All right. So I'm gonna put out a hey online people, if you have any last minute questions, do start getting them in. I like to give you guys a heads up beforehand because you are living in the past since stream delay is a thing.
Wow, how many light years away?
Usually it's no more than 30 seconds,
Okay.
but I like to give them a little bit of time because typing takes longer than speaking,
Okay.
at least for me.
Here's a fun fact. The sun is 8 light minutes away from us. So when we see this, if the sun was to explode, it'd take like 8 minutes for us to see the light. That would show us that.
Or the lack thereof
Just saying.
light.
Well, you'd see a pretty bright flash first. Yes.
We'd probably all. I like my microphone there. All right. Question out here. Bueller. Oh, perfect.
So going back to Oumuamua, you said it got really close to the sun. Did it get like so close that it would have gotten hot from the sun? And if it got so close that the temperature would have increased, would that have also increased the speed because ice would have melted?
Well, speed does increase as you get around the sun, and the temperature also increased. And one of the reasons why we're not calling it a comet is because when comets get closer to the sun, they get longer and longer ion tails and dust tails because it's a icy snowball. And so as it melts, we see the two tails. The ion tail always points directly away from the sun, and the dust tail, which heavier particles, is more an indication of the motion of the comet around the sun. So yeah, it would get warmer, and that's why one of the theories is that there was some ice on there, and there were hydrogen jets that were adding to the velocity that we were measuring on Oumuamua. But again, we're not really sure. It happened very quickly. It was about, I think it was like like about 25 or 30 million miles from the sun when we actually saw that, when we detected it. So it was between us and the sun when we detected it. We didn't like see it coming from far, like from Jupiter, and then track it. We just said, what is this? We actually see it, and before we knew it, it was gone. So we had, all of a sudden, telescopes around the world focused on it, and we tried to gather as much data as we could. And the data was such that at first it was an asteroid, then it was a comet, then it was an asteroid, then it was a comet. And I'm not even sure if they're calling it a comet or an asteroid anymore. I think they might just be calling a what is it object.
Interstellar debris.
Yes.
All right. So before I get to the next question online, this online comment made me giggle a bit about the galaxy you showed, where you had all
Hobbes
the
object?
older stars and then the blank space and all the younger
Yeah.
stars.
Yeah.
Looks like the older stars made themselves a gated community.
Okay.
No one below the age of 60 billion years old or something like that. I don't know the ages of stars, so I'm making numbers off the top of my head. Anyone who might actually know ages of stars. All right. So our next online question: does the accretion disk emit the radiation?
Yes. And that's why we were able to photograph it in that because what you were looking at was the accretion disk. Yeah, light does not leave the black hole, so we saw a big void in the middle of the accretion disk, but it was the accretion disk that we were photographing. Imaging. I gotta keep saying image. I'm an old. When I started astrophotography, I used film cameras, so I'm always saying film. There's no film in the Hubble Space Telescope or the James Webb. There's
But-
just sensors, CMOS.
Aren't you so
the
much happier now that you don't have the constraints of film?
Oh my goodness, yes. Yeah, film was definitely a very masochistic endeavor. Digital is amazing. You take 50 or 100 images, and there's software that lets you put them all together and get amazing images that you could never get in film.
All right. Any questions out here? All right. So it looks like our last online question is, why does light get sucked into the black hole? Because, you don't think of light as
Particles?
something physical.
Yeah, light is physical. It can't leave the black hole. And yeah, if you really want to give yourself some intellectual constipation, read about light waves, particle versus waves, and just delve into quantum mechanics while you're at it. It's amazing.
Physics.
Yeah, start with something that says a beginner's guide to whatever you want to.
Yeah, I think there's probably one of those yellow and black books, KISS, Keep It Simple.
Right.
Everyone knows what the last S is, but I try not to go there. So any last minute questions here before we wrap
I
up?
thought there might have been one way in the back. Is there one back there?
Oh, sure,
Okay.
we can.
I'm
Allow
sure I
you-
can come up with a random answer.
42.
There you go. Good
I was-
answer.
I was just curious if you know what's the largest star that we've ever observed and how big it is.
Oh boy.
Kind of just like a gee whiz question.
Yeah. Come next month. I've got a scale going all the way up to the largest star, and I can't tell.
Isn't it like
what is it?
Antares?
No, they're much bigger than Antares.
Oh no, Betelgeuse is bigger than Antares.
Yeah, no, this goes. I'm sorry. I can't think of the name.
I
of it.
have that YouTube video playing in my head because I've seen it so many times and I can't think of it either.
But but Google that. You'll get the answer immediately. It's stunningly huge. You have stars like Betelgeuse where if it was where our sun is, it would fit into Mars, but the largest star goes out to Jupiter. Jupiter would be inside of it if it was where our sun is. I just can't remember the name because it's all Greek letters, and I don't remember which ones it was.
It's all Greek to me.
Yeah, it's all Greek to me. Sorry.
All right. So thank you again, Walt, for another wonderful presentation.
Thanks for coming.
Thank you
Yeah,
all for
and thanks
joining
for
us not
watching.
only here, but online. If you think of any questions, do feel free to reach out to us. Our website's always available, as well as our Discord. Also, if you want to go back and review videos or you can't make it here, you can always catch us when we live stream on YouTube or Twitch. Or we also keep our old presentations archived on YouTube. So do check us out there. Hit those like and subscribe buttons, online people. I noticed a couple of you did, and we are very appreciative. And with that, everyone, have a good night, clear skies, and good seeing.
Yeah.
Unlike tonight.
Please come back for clear skies.